So one thing that occurs is that um, if we have a high nominal stress and a stress concentration factor, then essentially, for lower life conditions, the stress concentration has less of an effect. So you see here, like this here is the line for something that's notched. This one is here. Here is just for a regular test specimen. And at the higher length, the higher lifespans, especially at the endurance limit, again, we have the full effect of the fatigue stress concentration factor. So the ratio of this to this would be the Kf. We have less an effect when we have higher stress levels and resultant lower life levels. That's essentially due to the fact that as if we have the stress concentration factor going on in a ductile material, what's happening is we can only get so high until we get to the point where it starts to yield, and then again the yield zone just keeps getting larger instead of necessarily having instead of increasing the stress at the crack tip. So you're not getting that the additional stress isn't having as much of an additional effect upon the lifespan of the component. So what you may be able to do is basically use a Kf prime instead of a Kf based upon what sort of lifespan you're trying to target. Now basically at a million, at 10 to the 6 cycles or more, your Kf should be just the Kf. Whereas some do recommend that it's possible to, at very low life situations, like 1,000 or less, you can kind of, the stress concentration, the stresses are high enough that you're getting that the stress concentration doesn't doesn't increase the stress much. It just it's yielding anyways, so you're getting minimal effect there. That's valid for relatively soft ductile materials. Other stuff like if you got say some cast irons, then the notches don't have a tendency to cause any localized increase in the stress, and that's just due to the fact that there's the inclusion of the high carbon flakes in the matrix that already cause their own localized high stress concentrations, so it's less of an effect. But you can it's reasonable to use the Kf prime instead of the Kf. It is less of a conservative estimate, so you may want to omit to doing so if you don't want to justify that design decision to your bosses. But it's certainly, depending upon what it is that you're trying to design for, it may be the difference between being able to do what you want and not. But as for kind of figuring out what our safety factors are, so if we're using the modified Goodman, essentially, so what we're saying is that if we have an operating point here at J, then the safety factor is basically the distance between O and J. Sorry, the distance between O and Q divided by the distance between O and J. So we need to kind of know the location of Q. So we got these two lines. We got this line right here, that line right there, the O to Q1. The equation for that line is y is equal to SA over m times x. And then we have the SN-SU line. So the equation for that one is SN minus SN over SU times x. So the intersection occurs where those two equations are where the y values for those two equations are the same. So we just equate those two, that one and that one, and then we solve for x. So we can solve for the x value at that intersection using the equation there. Sn over Sa divided by Sm plus Sn over Su. Now our safety factor again is those distances there. It could also be like, because of similar triangles, it could also, because this angle between O and J and O and Q is the same, that ratio could also just be x divided by Sm. So our x divided by Sm is our factor of safety. So just take this equation, divide it by Sm to get our safety factor. And that's a bit of a pain in the ass to work with. So if we invert it and multiply things out, we get this equation here, just by multiplying the Sm through to these and then dividing by Sn. And then we can cancel out some terms here. So we can cancel out this Sm and Sm term here, and we can cancel out this Sn and Sn term here, and then we're left with 1 over the safety factor of safety is equal to Sa over Sn plus Sm over Su. So that'll be if our operating point is in a position where the line is going to intersect this Sn-Su curve line first. The other condition would be is if we're somewhere over here and that line is going to intersect our SY curve first. So I'm not going to go through a similar derivation here. The equation we get out is the exact same equation as we had the other one, except we're replacing the the Sn and Su terms with Sy, because that's the equivalent values on both of those. So if you have an operating point, if you don't know which line is going to intersect first, then basically what you need to do is you just need to do your calculation for both of these. You do your calculation using both of these equations, and then you're going to be use the smallest of those two. So introducing stress concentration into things. Obviously, stress concentration comes into play too. So it's generally going to be recommended that you use the fatigue stress concentration factor and multiply it by both Sm and Sa. So some authors recommend only using the Kf on Sa, but I would, it's certainly less of a conservative estimate, and I don't think it's necessarily always justified. So that's for bending and axial loadings. If you also have the torsional, if you're working with just a torsional loading, then you can keep everything just in torsion. So that'll essentially just be you using Su for shear, and then an Sn for shear. So basically, when you go back to kind of the first, we go back to the calculation for the Sn, we're basing our Sn upon Sn prime, Cl, Cg, Cs, Ct, Cr. Maybe we didn't talk about Ct. Ct's temperature, but we're going to omit that for the time being. So the Cl is our loading factor. So basically, the CNS that we'd be calculating would be based upon the loading factor for torsion. And then as for the shear strength of your materials compared to the regular ultimate strength. So the shear ultimate strength for steels is typically about 0.8 of its ultimate strength. The shear strength for other materials is typically about 0.7 compared to the typical loading, a tensile loading. And then again, you're just getting your KFS from your KTS and your QS. So again, from the chart in juveniles, like I said, like I showed the other day, when we're using, if we're using just torsion, then you're picking which line you're using based upon these values here. And then, of course, pick your KTs based upon these charts. Again, also in juveniles, and those are going to be chapter 4. Now, the next thing you're probably going to ask, hey, what if we don't have just bending or just axial or just torsion? What if we have a loading condition where there is more than one? Well, then I think it's pretty clear that we can find some sort of equivalent. So basically what this formula does here is it goes and takes your various shear and amplitude and so on and so forth in axial bending and torsion, and it converts it to the basically kind of solves for the prime prime stresses and converts it to an equivalent in bending stress, kind of like an equivalent von Mises equivalent for bending stress instead. So everything that you kind of combine together can be represented as an equivalent amplitude, that's what E stands for, an equivalent mean of the stress. And then your failure criteria here, that's just based upon, so we got that one there, and we're also going to have, our SM, SA over SY is equal to 1 over FS, because again, our Goodman criteria has both. So yeah, use both equations. Should have included that in the slide. And our Sn here that we're using here, again, this is transforming it to a bending equivalent. So the Sn is going to be based upon our Sn is going to be based upon using a loading factor of 1. So again, important factors. So if we can use these if we're applying everything separately for torsion or for bending. If not, again, use our use the failure criteria that transforms everything into the equivalent. And again, always when you're doing these, this is the equation you use. If you know that it's going to hit this line first, if you don't know it's going to hit that line first, it might hit this line first. So you just need to replace all those with the equivalent yield strength. So our SUS becomes the SYS. Our NS becomes the SYS. And yeah, that's it for now.